Okay, so this afternoon we want to look at a series of steps which are in mathematics called Gauss elimination. So Gauss elimination basically is how you obtain your upper triangular system or how you obtain your lower triangular system. So you can do Gauss elimination, then you go through these particular steps which you're going to go through, then you'll be able to change your coefficient matrix, your matrix of coefficients, because you're trying to work out a system of linear equations. So you end up having a coefficient matrix, then you're going to be able to convert your coefficient matrix into an upper triangular system, which then you can work out, then you can use back substitution to solve for the unknowns. So when we met, when you're looking at the triangular linear systems, we were saying to say, assume that somehow, using whichever method you have used, you have your upper triangular systems. Your upper triangular system, whether it's lower triangular or upper triangular, then your triangular system, whether it's upper or lower, then how are you going to work it out? So we saw that you could solve a triangular system, a upper triangular system using back substitution. We also saw that you could work out an upper triangular, lower triangular system using forward substitution. So in this particular lesson, we're going to be using back substitution. But before we do a back substitution, we need to make sure that we convert our system of equations into a form which is suitable for back substitution. And that's where this process, this step, crucial step comes in, which is what we are referring to as Gauss elimination. So the whole objective of this particular step, which is Gauss elimination, is we are going to have a system of linear equations. As usual, you have n equations with n unknowns, and those n equations with n unknowns, you can write them in this fashion. You can write them as ax is equals to b. Then we want to change, we want to convert this ax equals to b, we want to convert it into a system ux equals to y. So we want to change our ax equals to b into ux equals to y. Basically, that's what we want to do. So we want to change our linear system into an upper triangular system, and we want to see which steps we're going to go through. Are we clear? And the steps which are going to go through, that is basically what's referred to as the Gauss elimination. There will be, so these steps which we're going to go through, we will be looking at a system of n equations with n unknowns. The following steps are the ones we're going to use. For example, there's something called an interchange. This basically means that you can interchange two equations. Then there's something called scaling. This is where you can multiply an equation with a non-zero constant, and if you multiply everything in that equation with a non-zero constant, the equation is still the same. So it's okay to change the order in which the equations appear. It is also okay, it will not change anything if you multiply one of the equations with a constant. And the other thing which we're going to do, which you're going to be doing, is something called a replacement, where we multiply one of the equations with a constant, then we add it or subtract it to another equation. That will also not change anything. So basically, these are the three steps which you're going to take. You can do an interchange, but in this particular case right now, we're not going to do an interchange. The only thing you're going to be doing is scaling and replacement. So interchange, we're not going to do it now, but we are going to, at the end, when you finish whatever we're doing, we're going to see under what circumstances you can do a raw interchange. Okay, so we are considering a system where you've got n linear equations. So you've got this one, 1, 2, 3, all the way up to n. So you've got n equations, and in these n equations, there are n unknowns. You've got x1, x2, x3, all the way up to xn. So you've got n linear equations with n unknowns. So this is the kind of system which we are looking at, and this is where you will be using your Gauss elimination, when you've got n linear equations with n unknowns. Anything else will not work. So if you've got a system like this, where your first equation is a11 x1 plus a12 x2 plus a13 x3, all the way up to a1n xn, this a11, these are what we call the coefficients. Then this x1, this x2, x3, all the way up to xn, these are what we call the unknowns. Then you've got your b1. This b1 is the non-constants. So for B1, the second equation, you've got A21 x1 plus A22 x2 plus A23 x3 all the way up to A2n xn equals to B2, and then you've got A31 x1 plus A32 x3 plus A33 x3 all the way up to A3n xn equals to B3. Then you end up having AN1 x1, AN2 x2, AN3 x3 all the way up to ANN xn equals to B9. So with a system like this, where you've got n equations with n unknowns, this system of linear equations can be rewritten as a matrix product AX equals to B. So where A is the A by n matrix of coefficients, so A is the n by n coefficient matrix. So in this A matrix A, which is what you have here, you have the coefficients A11, A12, A11, A12. It is supposed to be A31, A13, all the way up to A1n, then A21, A22, A23, all the way up to A2n, then A31, A32, A33, all the way up to A3n, then AN1, AN2, AN3, all the way up to ANN. So this is your matrix A. Then the unknowns, this is a column matrix of n by 1. So you've got x1, x2, x3, all the way up to xn. Then this B here is the column matrix of the constants B1, B2, B3, all the way up to B4. So it's possible that your linear system of n equations with n unknowns can be written in this fashion, like this. Are we clear up to this point?
Yes, sir.
Okay, next, what we are going to do is we're going to create a new matrix based on A and B. So we're going to create a new matrix based on A and B. So the matrix A is this one. So using this matrix A and using the matrix B, we're going to create a new matrix, which by putting together, like the way you, I don't know, the way you make a sandwich, by putting this matrix and this matrix next to each other. So we're going to create a matrix which is referred to as an augmented matrix. And the augmented matrix is basically denoted like this. So it's a matrix where we are combining matrix A and matrix B. Matrix A and matrix B are the ones which actually have numbers which make any sense, but when it comes to X, these are just unknowns and you can always find them anytime. So the matrix we're going to create is called an augmented matrix. In this augmented matrix is going to end up having n rows times n plus 1. So the augmented matrix AB, we're going to write like this. So AB, augmented matrix, this is going to be A11, A21, A31 up to ANN. Then you're going to add, this is supposed to be a straight line, but it's not possible to type a solid straight line with the software I use. So you, on the other end, the other column, you're going to end up with B1, then A21, A22, A23, all the way up to A2n, then B2, then A31, A32, A33, all the way up to A3n, then B3, then AN1, AN2, AN3, ANN, all the way up to the end as BN, like this. So basically, this is what you end up with, and this is what is referred to as an augmented matrix. Are we clear on how you construct this augmented matrix? You have to construct this kind of a matrix where you have the coefficients and the B's put side by side. So on this matrix, this is the matrix where we're going to do the scaling, this is a matrix where we're going to do the interchange, and this is a matrix where we can do, we will do the scaling, the replacement, and also, if possible, you can do your, your interchange. Okay, so the operations we're going to carry out with that matrix are basically, as we have explained, an interchange. Now, the first time we talked about these was in terms of equations. Now, what we have now are not equations. What we have now is a matrix with rows, with these rows, the first row, the second row, the third row, all the way up to the nth row. So what we have now are no longer equations, but what we have is a matrix. So when we talk about what kind of operations, what kind of things we can perform here, then we're talking about an interchange. When you talk about interchange, you're basically talking about switching the rows. When you talk about scaling, you're simply talking about multiplying a row by a non-zero constant. And when you're talking about a replacement, you're talking about multiplying a row with a non-zero constant, and after that we subtract this particular row from a particular thing. For example, if you want to modify a particular row, number R, row R, so this is a row which you want to modify. But what you're going to do is you're going to work out a non-zero constant, which is M, from what you have in R and what you have in row P. So this constant, which is what you're calling a multiplier, so you're going to be working out this constant, which is what you're calling a multiplier, or which is what is called a multiplier. Then you're going to multiply this non-zero constant with the row P. So if there's a row P somewhere, then you've got this number, M. You can multiply M times row P, then you get a modified row P because you have multiplied with everything in that row with a number M. Then you can subtract it. Usually we tend to subtract your modified row M, row P from this particular row. Then you're going to end up modifying this row, and that's what you're going to keep. So basically that's how a replacement process works, but I think it's going to be more clear when we actually start doing this. Okay, now there is the idea of something called a pivot row. Now the pivot row in this particular case is this row we are using, row P. The P is for pivot. Okay, so the row you're going to use, you're going to multiply with some non-zero constant so that you can modify some particular row. That is what is called the pivot row. Now in this row P, you do not use everything. There is a number you're going to choose. You're going to usually the diagonal element in that particular row. You choose a diagonal element in that particular row, and that diagonal element is what you're going to use to work out this multiplier. So the diagonal. So if you choose a particular row to be the pivot row, which is what you're going to use for modifying the other rows, then the diagonal element in that particular row which you have, that is what is going to be referred to as a pivot element. That's what you're going to use to work out this multiplier based on the number of the row you're trying to modify. So you put a number here, and also based on the number of the pivot you're going to put there. So you have to indicate how did you come up with this multiplier. You have to tell us how did you come up, which multiplier is this, how did you come up with it. Oh, I came up with this multiplier by using row number 2 and row number 1. So you need to indicate which row was being modified. That's what the R is here. And which row is the pivot P. That's what the P is there to do. Okay. So with this information in mind, so basically again, what we are trying to do with Gauss elimination, with back substitution, is the following. You have a coefficient matrix A, which is an n by n matrix, and this matrix is something called non-singular. Basically, what that simply means is that you get a matrix A, then you change it into an upper triangular matrix or a lower triangular matrix. Once you do that, then when you multiply the diagonal elements of your triangular matrix A, those diagonal elements are not supposed to be equal to 0. So basically, the determinant of this particular matrix is not equal to 0. So if the determinant of a matrix is not equal to 0, then you call such a matrix a non-singular matrix. Otherwise, if a determinant is equal to 0, I think such a matrix what is referred to as a singular matrix. Okay. So you have got a matrix a matrix A, which is n by n, and this matrix A, which is n by n, with whatever other things, you can write it as AX equals to B. So what you want to do is you want to convert this AX equals to B, you want to convert it into an upper triangular matrix multiplied by X and equals to Y. So in this particular case, in your upper triangular matrix U, you have to make sure that all your diagonal elements, A, K, K, these are not equals to 0. But because if your diagonal elements are equals to 0, then it simply means that your determinant, if one of your diagonal elements equals to 0, it simply means that your determinant is going to be equals to 0. And if your determinant is equals to 0, it means that you can't solve this matrix and you can't find a solution. So if all your diagonal elements in your upper triangular matrix are not equals to 0, then the determinant will not be 0. Then it means that you can work out this particular system using back substitution and work backwards so that you can find your values of X. Okay, so how is this going to work? So we've got an example which we are going to work through, and this example is going to help us understand what we are trying to do. Now, one of the things which we are going to do in this particular example is the first thing we're going to do. There are 3 steps we're talking about. There's 3 steps you can use to manipulate a matrix like this. We have said there's an interchange of the rows. There is scaling, where you multiply one of the rows by a constant. There is also a replacement, where you multiply a row, your pivot row, by a multiplier, then you subtract this pivot row from a particular row. Now, for now, we're only going to focus on 2 steps. One is scaling, and the other one is replacement. We will not look at interchanges. Okay, so we're just going to be doing Gauss elimination without doing a row interchange. There are circumstances under which you can do a row interchange, but for now, our focus should only be on how do we do this process. How do we carry out this Gauss elimination process? Okay, so we are going to use the following system of linear equations: x1 plus 2x2 plus x3 plus 4x4 equals to 13. Then 2x1 plus 0x2 plus 4x3 plus 3x4 equals to 28. Then 4x1 plus 2x2 plus 2x3 plus x4 equals to 20. Then minus 3x1 plus 2x2 plus 3x3 plus 2x4 equals to 6. So what we have here, as you can see, there are 1, 2, 3, 4. We've got 4 equations, and in these 4 equations, there's 1, 2, 3, 4. So you've got 4 equations with 4 unknowns. So whenever you're trying to solve a linear system with Gauss elimination, the first thing you need to check out is how many equations do you have. The number of equations you have needs to match the number of unknowns. Are we clear? We are going to mention this over and over because it's a requirement, because a step like Gauss elimination is used all over the place. It can be used in situations which you are not even aware of. As long as you are aware of, you know what's prevailing, then you can do Gauss elimination. Okay, so the first thing we're going to do is we are going to express this system of linear equations as a matrix product, AX equals to B. After expressing it as a matrix product AX equals to B, then we are going to construct our augmented matrix AB. Then from this augmented matrix, we're going to go through steps, Gauss elimination steps, which will end up giving us this upper triangular system UX equals to Y. Then from this upper triangular system UX equals to Y, we are going to work out our X.
Excuse me, sir.
Yes.
Yeah. People have been complaining in the group to say you're not admitting them.
I can't admit when there is no request. How do you expect me to admit people when I can't see any request? That's not how this thing works.
Okay, let me tell you.
No, that's not how it works. So people can just complain that they're not being admitted when you have not asked to enter a meeting. It's the internet. So if people don't ask to get into a meeting, then you can't be admitted. If someone asks to get into a meeting, then it's going to notify me, say, oh, there is someone who wants to get admitted. That's how this thing works. Okay, so our system, when we write it in form of a product, AX equals to B, so we're going to end up with the following. We're going to end up with 1, 2, 1, 4, then 2, 0, 4, 3, then 4, 2, 2, 1, then minus 3, 1, 3, 2. So this is going to be a coefficient matrix A. Then the unknowns are going to be x1, x2, x3, and x4. Then equals to your B, which is going to be 13, 28, then 20, and 6. So in this particular setup, our A is 1, 2, 1, 4, 2, 0, 4, 3, 4, 2, 2, 1, and minus 3, 1, 3, 2. And your X is x1, x2, x3, x4. Then your B is 31. Yeah. So someone has asked to be admitted, then you admit them. That's how this thing works. Not just people sitting, then you say you need to be admitted. Okay. Then your B is 13, 28, 20, and 6. So with this information, with the A, which is our coefficient matrix this way, A here, and our B, which is this one here, our B. We construct our augmented matrix AB, and that's going to be 1, 2, 1, 4, then bar here 13 from the B. Then so this bar here indicates the separation between the matrices, the separation between A, matrix A, and matrix B. This we're going to call our row number 1, then 2, 0, 4, 3, then they separate here, that's a separator, then the 28 from matrix B, then 4, 2, 2, 1, then the separator, the 20 from matrix B, then minus 3, 1, 3, 2, then the separator, 6. So this row here, this is row number 1, then this bit here, this is row number 2, then this bit here, this is row number 3, then this bit there, that's row number 4. So we have our augmented matrix, which is made up of 4 rows and 1, 2, 3, 4, 5 columns, as is supposed to be the case. Are we clear on the construction of the augmented matrix? How we construct the matrix?
Yes, sir, clear.
Okay. The next thing we're going to do is, what we actually want to do here is the following. We want to make sure that row number 1 remains the way it is, unchanged, because we're trying to make an upper triangular system. Then this one here, this is the diagonal element. This is A11. Okay, that's the diagonal element A11. We want to make sure that everything below this diagonal element 1, everything becomes this 2. We change this 2 into a 0. We change this 4 into a 0. We change this minus 3 into a 0. So everything below the first column, below the diagonal of the first column. So we look at the first column, the diagonal element is this one. Then everything below here, the diagonal, we want to change into a 0. Then we come to the second column, this one. The diagonal will be at this particular point. Everything below the diagonal, we want to change into a 0. Then we come to the third column, this one. The diagonal is this one here. Everything below there, we want to change into a 0. So we want this number to become a 0. We want this number to become a 0. We want this one to become a 0. We want this one to become a 0. We want this one to become a 0. We want that one to become a 0. So once we succeed in doing this, in changing these numbers below the diagonals, below the diagonal of matrix A, once they become zeros, then we have achieved our objective of converting A into an upper triangular system. But in the process of doing this, we are also going to be modifying this row. So instead of having B, what you're going to end up with after we are done with the modification, what you're going to end up with, you're going to end up with a modified version of B, which is what we are going to call Y. Are we clear?
Sir, repeat that.
I am saying that once we are done modifying A, in the process as we'll be modifying A, this B is also going to be undergoing modification. So by the time we are done completely, this one changing into a 0, this one 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 into a 0, we will not have the same B this side. We will have a different matrix, a column matrix this side, after the separators here. That matrix which you're going to end up having is what we're going to call Y, matrix Y. Because remember what you have said is, by the time we end up with our modification, we need to end up with this. We need to end up with this upper X, then Y. So as we are trying to get this, then your B is also going to be modified. In every step you do, you modify B. So at the end of the day, you're going to end up with Y. So this is going to be easier if we now show how the whole thing works. So the first thing we're going to do is we need to select a row we are going to use to eliminate the elements which we need. So we choose the first row. Usually we choose the first row, even though in this particular case our first row is not the best choice, as we're going to see after we are done. We choose the first row as our pivot row, and in this pivot row you choose the diagonal element as your pivot element. So you choose the row P you're going to use to eliminate things, and you're also going to use to come up with your multipliers, and you choose the diagonal element, in this case A11, as your pivot element. So we have chosen row number 1 as our pivot row, and we have chosen diagonal element A11 equals to 1 as our pivot element. So what we're going to use this for is to work out our multipliers. So we're going to get this 1, we're going to divide it by 2, so it gives us a multiplier, which we're going to use for modifying row number 2. We're going to get this number, we're going to divide it by 4, so we'll divide 2 by 1, 4 by 1, minus 3 by 1, so that we can come up with these multipliers. Okay, so to eliminate, so the first thing we want to do is we want to eliminate this number in the first column of row number 2. So to eliminate the element in the first column of row 2 using row 1, we calculate a multiplier M21. Okay, now remember what we said earlier. The first number is the error, which is the row you want to modify, which is this one, row number 2. That's what the 2 is doing here. Then the 1 is for the pivot row. Which one is the pivot row? There, row number 1. That's what these numbers are, M21. For the 2 is for the row you want to modify, the 1 is the pivot row. So the way it works is M21 is going to be equals to, you want to divide this number by that number. So that's going to be A21 divided by A11. Are we clear? A21 divided by A11. So that's going to be 2 divided by 1. That's going to give you a 2. So this is the number you're going to multiply. This is a value you're going to multiply your pivot row with, then subtract from row number 2. So basically what you're going to do is the following. You're going to have row number 2 will be equals to M21 times row number 1. So your multiplier, which you have worked out, which is this one here, 2 times the pivot row, which is row number 1. So you're multiplying your 2 times this first row, all of it. Then whatever you're going to get, so you multiply your multiplier M21 times the first row, whatever you're going to get, then you subtract it from row number 2. The whole process, the hope is when you do this, when you do things this way, you're going to get rid of this. So this one should turn into a 0. So at the end of the day, when you do that, you're going to end up with a modified row number 2. So how does that work? So we pick up row number 2. This is row number 2 here, and that's what you've put here. So this whole thing here is row number 2. You've got the 2 here, you've got the 0, 4, 3, 28. So that's what you have here, 2, 0, 4, 3, 28, then minus the multiplier, which is what you have here, which is the 2, times the row number 1, which is 1, 2, 1, 4. 1, 2, 1, 4. So that's what you have here. 2 times 1, 2, 1, 4, then there's a 13 at the end. So what you're going to do next is this multiplier, which is what you've worked out as 2, you multiply this times everything inside here. So 2 times 1 will give you 2, 2 times 2 will give you 4, 2 times 1 will give you 2, 2 times 4 will give you 8, 2 times 13 is going to give you 26. So you end up with this. So this is your modified row number 1. Now here is where the things are going to happen. Why did you choose A21? Because we wanted to get rid of A21. So now it's going to be 2 minus 2, it gives you 0, 0 minus 4, it gives you minus 4, 4 minus 2, it gives you 2, 3 minus 8, it gives you minus 5, then 28 minus 26, you get 2. So this is now our modified row number 2. As you can see, the first element in row number 2 is 0. So we have managed to change our 2 in row number 2. We've managed to turn it into a 0. In the process of doing that, we have also changed the element in B. It was 28, now it's 2. So you can see that there's a modification which is happening to the matrix B also. Are we clear?
Yes, sir.
Next, we need to make everything below the 1. We need to turn the 2, we need to turn the 4, we need to turn the 3. All these in the first column below the diagonal, we need to turn them into zeros. So next, we're going to modify this row number 3. That's the row we want to modify. We want to modify row number 3, and we're going to use row number 1 to do that. And with row number 1, we already have our thing. So row number 1, that's what we're going to use, and row number 3. So with row number 3, what we want to turn into a 0 is this guy. We want to turn the 4 into a 0. So we select the 4 as the element you're going to use in row number 4 and row number 3 to work out the multiplier. So it's going to be A31, which is equals to 4. So M31, so M, the row, 3 is for the row, then 1 is the row of the pivot. So 3, the row we're modifying, 1 is the row of the pivot. Is going to be equals to A31, which is the element you want to turn into a 0, divided by A11. So that's going to be 4 divided by 1, and you're going to end up having 4. So your multiplier in this case is going to be a 4. So you always put the element you want to change into a 0 here. So when you do that, so we're trying to modify row number 3. So we're going to end up with the following. So we're going to end up with row number 3 is going to be equals to the multiplier M31 times the pivot row number 1. When you do this whole thing, it should give us a modified row number 3. So row number 3 is 4, 2, 2, 1, 20. So row number 3, if you go back and have a look at it, it's here. It's 4, 2, 2, 1, 20. So 4, 2, 2, 1, 20. So that's what we have there. So we have 4, 2, 2, 1, 20 as our row number 3 minus then M31. M31 is the multiplier, so that's going to be 4 times the row number 1, which is 1, 2, 1, 4, 13. So here we multiply 4 times 1 is 4, 4 times 2 is 8, 4 times 1 is 4, 4 times 4 is 16, 4 times 31 is 52. So this is our the pivot row we have modified. Then we use this modified pivot row, we subtract it from row number 1, so you're going to end up having 4 minus 4 is going to give you 0, 2 minus 8 you're going to get minus 6, then 2 minus 4 you're going to get minus 2, then 1 minus 16 you're going to end up with minus 15, then 20 minus 52 you're going to end up with minus 32. So as you can see, again, what was the first element in this row number 3, which was a 4 here, has now been successfully turned into a 0. In the process of doing this, of course, there has been some modifications in all these other elements. Is that clear? Are we clear?
Yes, sir.
Next, the other thing we want to modify, apart from the 4, we want to modify the minus 3 at the bottom. This one. We want to modify this. So what we want to modify is row number 4. If you're modifying row number 4 using row number 1's multiplier, is going to be 4. It's going to be what is 4, then 1. So M41. And for us to work out M41, we need this minus 3, which is A41 and A11. So we're going to work out that multiplier. So when you do that, we're going to end up with the following. So you're going to end up with here M41. So M41 is going to be equals to A41, which is the minus 3, divided by A11, which is the diagonal element in that particular column. Then that's going to be minus. So you always divide, you put on top the element you want to get rid of, then at the bottom you put the diagonal element in that particular row. So always at the bottom the diagonal element in that particular row, then on top the guy you want to get rid of. So we want to get rid of the minus 3 so that we change it into a 0. So minus 3 divided by 1, we're going to end up with minus 3. So we're trying to modify row number 4. So we're going to have row number 4 minus the multiplier M41 times row number 1 like this, And when we do this, we hope to get a modified row number 4. So a row number 4 which has been modified only once. So when you do that, row number 4 is minus 3, 1, 3, 2, 6, then minus, then the multiplier is minus 3 times row number 1, which is 1, 2, 1, 4, 3. So there is a minus and a minus, so we're going to end up with a plus here. Then there is a 3 times 1, then there is 3 times 2, then there is 3 times 1, there is 3 times 4, then there is 3 times 13. So when you do that, you're going to end up with the following. So 3 times 1, so 3 times 1 gives you this 3 here, 3 times 2 gives you this 6 here, 3 times 1 gives you this 3 here, 3 times 4 gives you this 12 here, then 3 times 13 gives you this 39 here. That's what you have here. Then row number 4 plus this. So you're going to have minus 3 plus 3. So minus 3 plus 3, minus 3 plus 3 gives you 0. Then 1 plus 6 gives you 7. Then 3 plus 3 gives you 6. Then 2 plus 12 gives you 14. Then 6 plus 39 gives you 45. So by modifying, by making sure that all the elements below the diagonal in the first column are equals to 0, we end up changing everything else in our respective rows. So we can reconstruct our single modified augmented matrix. And how do we show how many times an augmented matrix has been modified? You put this thing here, and you put the, whether it's an apostrophe, you put 1 to show that this thing has been modified once. So the first row was not modified, so it just remains the way it is. 1, 2, 1, 2, 1, 4, then 13, row number 1. Then here, the second row, as you can see, the first element here has been modified. So 0, minus 4, 2, minus 15, minus 5, then 2. So this one, row number 2, has been modified once. Then the third row, again here is 0, minus 6, minus 2, minus 15, minus 32. So this one has been modified once. Then the fourth row, 0, 7, 6, 14, 45. You can see that this fourth row has been modified once also. So we are getting there. We have managed to make sure that every element below the diagonal element 1 has been turned into a 0. Are we clear?
Yes, sir.
So this is part of the step. The next step is we need to make sure that the other diagonal element is this one, the minus 4. This is the other diagonal element, the minus 4. We need to make sure that below this diagonal element, second column, we move to the second column. The second column is this one. Everything below the diagonal, which is the diagonal is minus 4, needs to be 0. This guy needs to be turned into a 0. This one needs to be turned into a 0. Then we move on to this row, third row. When we move on to this, we move on to the, so first column, the diagonal element is this one. Everything below the diagonal element has been turned into a 0. Then we move on to the second column. Enter the second column, the diagonal element is this one. We want to make sure that everything below the diagonal is turned into a 0. Then we move on to the third column. Third column is this one. The diagonal element is this one. We want to make sure that everything below the diagonal is turned into a 0, which is this one. Then fourth column, the diagonal element is this one. There's nothing to do there. So once we carry out these steps, then we will manage to do our thing. So we move to the second row. So to move to the second column, which is this one here, the diagonal element is the one you have selected here, is the one you have highlighted here. This row, which is row number 2 modified, is what we are going to choose. The second row is what you're going to choose as the pivot, as our new pivot. And the purpose for choosing this as a new pivot is because we want to make sure that this minus 6 here and the 7 here, they turn into zeros. Are we clear? Are we clear?
Yes, sir.
So in each step, we want to make sure in each step, we start with the first column. Everything below the diagonal 0. Once we are done with that, we move on to the second column. Where is the diagonal? Everything below the diagonal, we want to turn into a 0. We move to the third column. Where is the diagonal? Everything below, we want to turn into a 0. So right now, our diagonal is here. So we choose row number 2. This one, this modified row number 2, we choose it as our pivot row. So row number 2 prime is chosen as our pivot row, and the diagonal element A22 prime, because why prime? Because it has been modified. A22 prime, which is -4, we choose this to be a pivot element. So we start using this. We start using this row number 2 and the number of row we want to modify for our multipliers. So what we want to do right now, we want to work out this multiplier based on this. So row number 3 and 2, so the multiplier is M32. Then we're going to work out multiplier M42. So when you do that, so multiplier M32, the multiplier M32, in your notes, I'm supposed to strike out this apostrophe here. So M32, so multiplier M32 is going to be equals to A prime 32, which is this one, the one we want to get rid of, divided by the pivot element A22 prime, which is the -4. So that's going to give us -6 divided by -4. So it's going to give me 1.5 as my multiplier. This multiplier 1.5, which is M32, I'm going to multiply this multiplier with the pivot row, which is this one, the row 2 prime. Then I'll subtract it from row number 3 prime. That's what we did. That's what we did previously, and that's what we're going to do here. So we're going to end up with the following. We're going to end up with row number 3 prime minus M32 times row number 2 prime. So when you do this, you're going to end up with the row number 3, which has been modified twice, and that's why the apostrophes are 2 here. So the 2 apostrophes indicate that this particular row has been modified 2 times. So when you do that, you're going to end up with row number 3 modified once, which is this one, 0, -6, -2, -5, and -32. So that's the row number 3 modified once, then minus the multiplier, which is 1.5, then times row number 2 modified once. So row number 2 prime, that's going to be 0, -4, 2, -5, 2. So you're going to end up with 1.5 times 0, so that's going to be 0. 1.5 times -4, that's going to give you -6. 1.5 times 2, that's going to give you 3. 1.5 times -5, that's going to give you -7.5. 1.5 times 2, that's going to give you 3. Are we clear? Then you subtract. So this is your modified, this is a result of you multiplying what is us here. This is a scaling thing. You are multiplying a non-zero number with a row. So this step is scaling. Then when you subtract our scaled thing from some other column, this is now a replacement you're trying to do. So you're trying to modify something, then replace it. We're trying to modify this and replace it with whatever is going to come. So we end up having 0 minus 0. This is 0 we have here. Minus 6 minus 6, you get a 0. Then minus 2 minus 3, you get a -5. Then you get a minus 15, minus 7.5, you get a minus 7.5, minus 32, minus 3, you're going to get minus 35. So this becomes our row number 3 modified twice. So you're going to end up with 0, 0, minus 5, minus 7.5, minus 3.5. So you can see our 6, which was here, has now been modified into a 0. Are we clear? So we move column by column. We start with the first column. Everything below the diagonal, you change into a 0. Once you have finished that particular bit, you move to the second column. Everything below the diagonal, you want to change into a 0. Then that's where we are right now. Okay. Then the other thing, so we have managed to change our minus 6 into a 0. The next thing we also want to do, we want to change this guy. We want to change the 7 into a 0. Now 7 is row number 4. It's in row number 4. Then our pivot element is in row number 2. So the multiplier we're going to be working out is M42, and we're going to do that by dividing 7 divided by minus 4. So our multiplier M42, our multiplier M42 is going to be equals to A prime, the modified once A42 prime divided by A22 prime, that's going to give you 7 divided by minus 4. You're going to end up with minus 1.75. So this is going to be your multiplier, and this multiplier is what you're going to multiply by. We're going to use this multiplier to multiply by the pivot row, which is our row number 2 prime times M42. Then whatever we're going to get, we're going to subtract it from row number 4 prime. So our M42 is minus 1.75. Then our row number 2 prime is what we have here. Then the multiplier itself is what you have here. Then row number 4 is what we have this side. Okay, so when you do that, as you can see, there's a negative here, negative, that's going to give you a positive here. So you end up with 1.75 times 0, it gives you 0 here. 1.75 times minus 4, you're going to get a minus 7. 1.75 times 2, you're going to get a 3.5. 1.75 times minus 5, you're going to get a minus 8.75. 1.75 times 2, you're going to get a 3.5, like this. So 0, minus 7, 3.5, minus 8.75, then 3.5 here. Next, we add 0 plus 0, gives you 0. 7 plus minus 7, you get a 0 here. 6 plus 3.5, you get a 9.5. 14 plus minus 8.75, you're going to get a 5.25. Then 45 plus 3.5, you're going to get 48.5. So with these steps, we have managed to turn our targets, the minus 6 and the 7, into zeros. And when you construct our double modified augmented matrix, basically trying to say that our augmented matrix has been modified twice now, you're going to end up, you've got this one, which was a pivot row. In this particular step we're doing, then everything below here and there, those things have been turned into zeros. Then, so we have done the same process for the first column, then you have done it for the second column, then you need to do it for the third column. Now for the third column, we are going to choose the third, for the third row, for the third column, we choose the third row as our pivot row. When you choose the third row as our pivot row, then we're going to choose the diagonal element A33 double prime, which is this one, to be our pivot element, and you're going to use this diagonal element to eliminate this one at the bottom, so that we end up having 0, 0, 0 here, 0, 0, and this one, so that it becomes a 0. And when you do that, we would have managed to make everything below the diagonal to be a 0. If you manage to make everything below a diagonal to be a 0, then you have your upper triangular matrix. And once you have your upper triangular matrix, hopefully you can relate this whole thing as ux equals to y, then we can move on from there. Okay, so we are going to choose the third row, this one, as our pivot row, and this guy as our pivot element. So our pivot element is going to be A33 double prime, which is minus 5, and we're trying to use it to eliminate this guy here. So this guy is basically row number 4 here, row number 4, which is what you have here. Then we're trying to use the third row, this guy here in the third row, to make a pivot to do the elimination. So our multiplier is going to be M43. So M43, your multiplier M43 is simply going to be equals to be the following. It's going to be equals to A43 double prime divided by A33 double prime. That's going to be 9.5 divided by 1 by minus 5. That's going to give you minus 1.9. This multiplier M43, then you multiply this multiplier times row number 3 double prime. So M43 times row number 3 double prime, then minus row number 4. So because we're trying to modify row number 4 and we're using row number 3 as our pivot, so this is going to be minus here. It's going to be minus here. Then M43, that's going to be minus 1.49, minus 1.9. So that's minus 1.9. Then times row number 3 double prime. That's going to be 0, 0, minus 5, minus 7.5, minus 13. Like this. Then the other bit, row number 4, that's going to be 0, 0, 9.5, 5.25, 48.5. So negative, that's going to be the plus which you have here, 1.9, then this whole thing here, which is what you have here, then 1.9 times 0, you get a 0, 1.9 times 0, you get a 0, 1.9 times minus 5, you're going to get yourself minus 9.5, then 1.9 times minus 7.5, you're going to get yourself 14.2, then 1.9 times minus 35, you're going to get yourself minus 66.5. So with that, we can add things, so you can end up having 0 plus 0, that's going to be 0, 0 plus 0 is going to be 0, 9.5 plus minus 9.5, that's going to be 0, 5.25 plus minus 14.28, that's going to be 9, then 48.5 plus minus 66.5, that's going to be minus 18, like this. So we can now write our augmented matrix, which has been modified 3 times, our triple modified augmented matrix, AB triple prime. So it's going to be 1, 2, 1, 4, then 3, that's the first row, then 0, minus 4, 2, minus 5, 2, that's going to be our second row, 2 prime, then 0, 0, minus 5, minus 7.5, minus 35, that's going to be row number 3, double prime, then 0, 0, 0, minus 9, then minus 18, that's going to be row number 4, triple prime. Now if you look at this, you notice one thing, this is an augmented matrix. The first part here, before the separators, this is simply an upper triangular matrix. This part, this is an upper triangular matrix. If you see, this is an upper triangular matrix. Are we clear?
Yes.
Yes, sir.
That's what we wanted. So we have got an upper triangular matrix this side. That's what you're going to call U. And this side, we have got a matrix which is not B, but it's B, but it has been modified. This is 13, 2, minus 35, 18. It's B, but it's been modified. And this is what you're going to call Y. So we write our augmented matrix UY, our upper triangular augmented matrix UY. So upper triangular augmented matrix UY is going to be this thing here, which is our triple modified AB augmented matrix, which has been triple modified. When you write your augmented matrix like this simply means that this is your U, this is your Y. So this whole augmented matrix can be written like this: UX is equals to Y. So you end up having your U this side, then your X, X1, X2, X3, X4, the unknowns, then your Y, which is this side, like that. When you do that, then you can try to expand and simplify. You multiply these guys with these, you multiply this with these guys, you multiply this with this, you multiply this with it, as we have seen how that's done. When you do that, so you multiply U and X, you end up with the following, end up with X1 plus 2X2 plus X3 plus 4X4 equals to 13, then 0X1 minus 4 X2 plus 2X3 minus 5X4 equals to 12 equals to 2, then 0X1 plus 0X2 minus 5X3 minus 7.5X4 equals to minus 35, then 0X1 plus 0X2 plus 0X3 minus 9X4 equals to minus 18. When you get rid of these zeros, since it's possible that they might not show up in the thing, you end up with the following, end up with X1 plus 2X1 plus X3 plus 4X4 equals to 13, then minus 4X2 plus 2X3 minus 5X4 equals to 12 equals to 2, then minus 5X3 minus 7.5X4 equals to minus 35, then you end up with minus 9X4 equals to minus 18. Are we clear?
Yes.
This is an upper triangular linear system, and we saw last week. Say, if you've got an upper triangular linear system, then you can work out such a system using back substitution. So we start with the last one. So with the last one, this one, last equation, so minus 9x4 equals to minus 18. So you're going to end up with x4 equals to minus 18 divided by 19. You're going to end up with x4 equals to 2. So work out that. Then using the x4 equals to 2, we work out in the second equation here. So when we work out the second equation, you're going to have x3 equals to minus 35 plus 7.5 x4 divided by minus 5. You put your x4 here, which is a 2 there, you end up with minus 35 plus 7.5 times 2 divided by minus 5. You're going to end up with x3 equals to 4. Then you move on to, now that your x3 is equals to 4 and your x3 is equals to 4 and your x4 is equals to 2, we are going to use these values in the second equation so that we can work out x2. So x2 is going to be 2 minus 2x2 plus 5x4 divided by minus 4. So you end up with x2 equals to 2 minus 2 times 4 plus 5 times 2 divided by minus 4. You end up with x2 equals to minus 1. Then finally x1, so we now have x2 equals to minus 1, x3 equals to 4, and x4 equals to 2. So we're going to use these values to work out x1. So your x1 is going to be equals to 13 minus 2 x2 minus x3 minus x4 divided by 1. So you substitute those values there. You're going to end up with your x1 being equals to 13 minus 2, then x1 minus 4, put there minus 4 times 2 divided by 1. You're going to end up with x1 equals to 3 over 1. What have I done here? x1 equals to 3 over 1. 3 divided by 1 equals to 3. So this is supposed to be 3 here. Make the correction. You make the correction in the notes. So this is supposed to be 3 here. So the notes are already on Moodle. So you make the correction there. Like this is supposed to be 3. Okay, so our x values, our matrix of x is going to be x1, x2, x3, x4. That's going to be equals to 3 minus 1, 4, and 2. So this is going to be our matrix of unknowns. 3 minus 1, 4, and 2. Are we clear on how things work? Is it clear?
Yes, very clear.
Okay. So far, with what we have been doing, the only 2 steps we've done are we have multiplied the pivot row with some number. So we have multiplied a row with some number. That's called scaling. We have also, after multiplying the pivot row with some number, we have subtracted that modified pivot row from some other column. That's called replacement. So you have done scaling and replacement. Now, when you are trying to change, you can. It's also possible that you can do an interchange of rows. You can interchange the position of rows. That's not really going to change anything. Your system of linear equation will still remain the same. Now, the process of changing rows, that is what is called pivoting. Okay. When you are changing the rows, that is what is called pivoting. Now, there are a couple of reasons why it's a good idea for you to do this. The most important reason is after you look, when you look at your rows, okay, you say, fine, I'm going to choose, because usually we choose row number 1 as the pivot row. If you look at your pivot row, if it's a first row, okay, then you're concentrating on the first column. So you're looking at first row, first column, which is A11. If you look at your pivot element, that's what this is. APP. A, the rows are the same, the row and the column are the same, then the P is for the pivot. If you look at your pivot element and your pivot element is equals to 0, if your pivot element is equals to 0 for your pivot row, you can only have a pivot element if you have chosen that row to be the pivot row. So if you have chosen a pivot row, then you look at the diagonal element, then that diagonal element, which is your pivot element, you're going to choose as a pivot element. If your pivot element is equals to 0, then it's not possible for you to carry out this process. Because once your pivot element is equals to 0, once one of your diagonals is equals to 0, then it's going to make the determinant of that particular matrix to be equals to 0. If the determinant of the matrix becomes equals to 0, then you can't work out the solution. And of course, there's a bit why you can't work out the solution is because if you recall very well, everything we're doing here, up here, we are dividing by this number, which is a diagonal element. You're dividing by that number, which is a diagonal element. You're dividing by all these numbers. So if your pivot element is equals to 0, then it will not be possible for you to do back substitution. Are we clear? Are we clear? You want to make sure that your pivot element is not equals to 0.
Yes, sir.
Yeah. So if your pivot element, so here's a criteria for trying to switch rows. The first reason why you should switch rows is that you want to switch rows if your pivot element is equals to 0. If your pivot element is not equals to 0, do not switch rows. On the other hand, if your pivot element is equals to 0, then you switch the rows. The row where you have chosen as your pivot, which has got a pivot element equals to 0, you switch it with the row below. Are we clear? You switch it with the row below. The other reason why you want to make sure that your pivot element, you want to interchange rows, is because you want to reduce errors. Now, if you look carefully, if you look very, very carefully at what you have done, you will notice that all our multipliers are greater than 1. If you look very carefully at the way we did our Gauss elimination, you will clearly notice that all our multipliers are greater than 1. The absolute value, the absolute value of our multipliers is greater than 1. Now that's not a good thing. Having multipliers which are greater in value than 1 here, minus 1.9, and the absolute value of this is 1.9, so that's greater than 1. You come where? Here. Minus 1.75. This, the absolute value of this is greater than 1. Here. Minus 3. Here. 2. So what I'm trying to show you here is, as much as I've used this example to show you how you should do Gauss elimination, I have done things the wrong way, because all these multipliers I have are greater than 1, and when a multiplier is greater than 1, what it basically means is that there's going to be more errors. So my solutions are not very correct. As much as they look correct, they might not be correct. Okay, so what you do is you need to make sure that you multiply, the multipliers you are using are less than 1 or equals to 1. How do you make sure that the multipliers you're using are less than 1 or equals to 1? So you create, here you are, this is your matrix product, AX equals to B, right? Here's your matrix product, AX equals to B, like this here. Then you create your augmented matrix. When you create your augmented matrix, this is what you have here. So you've got 1, 2, 1, 4, 13, you've got 2, 0, 4, 3, 28, you've got 4, 2, 2, 1, 20, then you've got minus 3, then minus 1, then 3, 2, 6. So you look in the first column here. You look in the first column, then you check which row has got an element in the first column which is larger than all of them, whose absolute value is larger than all of them. In this case, this is going to be row number 4. So row number 4, the magnitude of row number 4, the absolute value of this value is greater than all of them. So the row, in this case row number 3, which has got a 4 in the first column, which has got a 4, which is larger than all of them, we make row number 3 become row number 1. So we interchange row number 3 for row number 1. Are we clear? You do this only once. You don't do it all the time. You just do it once. Just for the first column. If you want to do it for the second column, you can try to do that, but usually it's not advisable to do that. So you just do the interchange only in the first column. So you look in the first column, say which row has got an element in the first column whose absolute value is larger than all of them. So you choose that one and you make that one become, in this case, row number 3. So we would make row number 3 become row number 1, and row number 1 would become row number 3. So we would have interchanged. The reason why you do that is the following. So when you start working out, so if you do the interchange here, say this guy becomes row number 1, then row number 1 becomes row number 3. Our pivot element will no longer be A11, but our pivot element would become 4. Are we clear? When our pivot element becomes 4, then you work out, you want to eliminate this. It's going to be A21 divided by A11. That's going to be, what's this? 2 divided by 4. That's going to give you 0.5. So your plan, as you are trying to do Gauss elimination, is to make sure that your multipliers are small. Okay? They should be less than 1 or equals to 1. So your multipliers need to be small. So when you do that, so you're going to end up with the following. So you're going to, if it's 0.5, so you're going to end up with 0.5 here. Then whatever it is you have for row number 1, then you carry out the process like that. So always choose in a particular row. When you are looking at each column, okay, when you're looking at each column and say, fine, here is the diagonal thing and everything below the diagonal, choose the ones, choose the elements that, choose the element below the diagonal included and below the diagonal, choose the element which is the greatest, then you choose that to become your pivot element and your pivot row. The row it belongs to, so that becomes your pivot row. Are we clear? Are we clear? Hello? When you do this whole thing of interchanging, you look at the first column, you see which row has got the largest number. Then the row with the largest number, you make it become your row number 1. So you look at the first column, which row has got the largest number in it, then you make that one become row number 1. That is called pivoting. If you only do it for the first row, for the first column, the step is called Gauss elimination with partial pivoting. If you do it for all, if you be switching all the columns, the rest of the columns, then that's called Gauss elimination with pivoting. So usually it's sufficient. It's usually sufficient to just do Gauss elimination with partial pivoting. Okay. Any questions? So by doing that, you'll basically be reducing the amount of errors which are going to be there. If there are no questions, we're done with Gauss elimination. Tomorrow we are not going to meet because yes.
The question.
Yes.
On the pivoting, the one that you're saying on switching parts, I didn't clearly get that part where you're saying when the other one is greater, then that's when you use. I'm kind of lost on that part.
You look at the first column. When you have the first time you create your augmented matrix, you look at the first column of your augmented matrix. Which row has got the largest number in terms of signs, not in terms of negative or positive? Which row has the largest number in terms of signs? Here, the first row is this one: 1, 2, 4, minus 3. Which row has got the largest number? It's row number 3, because the largest number in the first column is 4. Are we clear?
Okay, sir.
So this row,
Yes, I've seen. Okay.
this row, you interchange it with the first row, so that row number 3 becomes row number 1, and row number 1 becomes row number 3. That will make sure that your pivot elements, your diagonal element will be the largest. Okay, you always have a diagonal element which is large. You always have large diagonal elements. Are we clear? So when your diagonal element is large, it will make sure that your multiplier will be less than 1 or equals to 1, and that's what you want, so that you reduce how many errors are in your solution. So there's a way of doing Gauss elimination. You can just say Gauss elimination, so you're doing things without doing any row interchange, or you can do Gauss elimination with partial pivoting, where you just interchange for the first column, or you can be interchanging as you go through, which is just Gauss elimination with pivoting. So the right way to do it is you make sure you look at the columns, the first column, which element is the largest, then you make that one your first row. So that's Gauss elimination with partial pivoting, because you're only doing pivoting for the first column. If you're only doing pivoting for the first column, we call that Gauss elimination with partial pivoting. If you're not doing any row interchange, it's just called Gauss elimination, like the one we did. If you're going to do pivoting for everything else as you go along, then you call that Gauss elimination with pivoting, full pivoting basically. Okay, so tomorrow we're not going to meet because I need to start running up and down. You know, school is, you guys are supposed to open, so I need to start doing this Ratsa business, road tax, insurance. I start tomorrow, then hopefully by Monday I can do the fitness stuff, or Monday or Tuesday I can do the fitness, so that I'm able to move around. You know, you can't pay any 100 quarter. If you've already paid 100 quarter, it's finished now. You have to pay the full amount, and I don't have the full amount to be giving the police or the government. So I need to do the road tax tomorrow. Insurance and road tax I'll do tomorrow. Then on Monday I'll go for fitness. So tomorrow we're not meeting. We'll meet on Tuesday, which is on 31st. Yes. In the meantime, the notes for these notes are already available on Moodle. The notes we're going to look at on Tuesday will be available on Moodle over the weekend. Once we're done with this topic, there will be another assignment. So for after each and every topic, there will be an assignment, so that I can make sure that people are understanding and are practicing what we needs to be done. Because these same things we're looking at, this is how your test is going to look like. This is how your exam is going to look like. In this particular course, you can know what your exam is going to look like. Everything, almost everything, whatever is in your assignments, those are the same things you have in your tests. Those are the same things you're going to have in your exams. This is one of the few physics courses where it's possible at this particular stage for you to get 100% in an exam. If you're doing your assignments, it might be even possible for you to get an A+. So please do your assignments, submit them. I've seen people have already started submitting. So do your assignments, submit them, attend class. Eventually, as we move forward and forward like that, when school starts, then we also start doing labs. And this course is very short. Already we have done what's this? We have done 2 topics. When we start next week, you're going to do probably in 2 weeks we'll finish a topic. So by the end of next month, we'll have done 4 topics, and the whole course basically has got about 7 topics. So next month will be September, then there'll be October, then there'll be November, but we'll basically be able to get done by the end of November. Okay. So yeah, and also I hope people have got their vaccines. Please get your vaccines. Okay, so see you on, not tomorrow, see you on Tuesday. Okay, so I've come to the end. Unless there is any question. All right.